Hi everybody, I hope this video finds you well. In today's video, we're going to be starting into a new chapter, chapter 4 from our textbook, and we're going to be doing that by working our way through section 4.2, which introduces you guys into the concept of a vector space. Now, before we get into the sort of content of the video, there are sort of three general comments I'd like to make about this sort of moment as we start this section 4.2 and also really start the second half of our class overall. First of all, as you guys can probably already tell by the title of this video, the sort of first section from chapter 4 that we're going to be doing is section 4.2, which does mean that we're skipping section 4.1. 4.1 in your textbook is a review of how to work with n-dimensional real-valued vectors, so vectors from Rn. You guys should have a lot of practice and sort of be pretty comfortable with working with those types of vectors from your work in your multivariate calculus course like 220, or like if you've done this in physics, you've worked a lot with vectors, or if you've just done it in geometry. Most of you guys are pretty comfortable with just normal sort of real-valued vectors. So we're going to be skipping section 4.1 and jumping right into what's sort of important for our course, which is section 4.2. That means if you want, you can take a glance at 4.1, but there won't be any sort of exercises or any content from that section that we directly need. The second sort of general comment that I'd like to make is that this introduction into vector spaces, and really this entirety of chapters 4, 5, and 6, really is going to be for a lot of you guys the sort of introduction to pure or theoretical mathematics. That means that a lot of the stuff we're going to be doing in these next couple chapters is going to be pretty abstract, and it's going to be a while until we see what use it's going to be for differential equations, which is where we started from. But I want to really sort of just tell you guys to sort of think about that the importance of this stuff that we're going to be talking about in vector spaces and then later on in chapter 5 and chapter 6 is important, not just because it'll eventually be used for something, but it's important from a theoretical standpoint. It's really an investigation into sort of the underlying structure in parts of mathematics. And in this case, it's going to be the underlying structure behind vectors and behind the linear operations. So it's a very sort of important moment because it's really your chance to start to think about these abstract and sort of pure mathematical concepts. The other thing that I wanted to sort of mention in terms of that transition to a more theoretical topic is that not only is it going to be sort of different material than a lot of stuff that you've seen before, the thinking that we're going to be doing is going to be very different. In a lot of your previous math courses, like in differential calculus and integral calculus, you sort of worked top down. You would learn a concept or a definition, and then you'd follow that as far as you could, learning more and more about what that sort of operation was or things you could do with it, etc. Right? In like differential calculus, you learn the definition of the derivative, and then you use that to talk about derivatives of different functions or rules for taking derivatives of complex functions or applications through optimization using the derivative. So you started with one sort of basic thing, this derivative concept, and then you followed it. That's sort of the logic that in most of your previous math courses you've been doing, and that's really been the sort of logic we've been doing in most of this course. But now we're going to sort of take a step back and actually try to understand properties and structures that are behind the scenes. The reason that your textbook puts that section 4.1 before this is to sort of remind you guys, okay, you know how to work with vectors that are just n-dimensional sets of real numbers, right? The geometric vectors. But what we're going to do in this section is learn what are the properties that are behind the scenes that make that structure work the way it does. And what other structures out there that we might have encountered, even though they don't necessarily sound like vectors, actually act the same way. So we're doing sort of a much more macro approach to mathematics in this section, learning the sort of behind the scenes information here. All right. Last sort of general comment I want to make before we get into this is that this section 4.2 that introduces you guys to vector spaces will be divided into 3 videos. And I highly recommend that if you get the opportunity that you should go through and watch all 3 videos sort of one after another. This is definitely a section that I think benefits from seeing all of the material sort of connected to each other. If we were doing this in class, we would take a good hour to an hour and a half to talk about everything so that you could see how all the different pieces relate. I don't want to upload like an hour and a half long video, so to make that a little bit easier, there will be 3 separate videos, but I recommend if you get the chance to watch them all in quick succession so that you can sort of see how all pieces that we're going to be discussing here really relate to one another. So, without further ado, and considering that we just said we don't want massively long videos, let's get into actually talking about the definition of a vector space. So, what is a vector space? Well, a vector space is a mathematical construct. And when you go to build a vector space, you need to begin by sort of building 4 separate things. First, what you need to do is you need to collect a non-empty set of objects, and we're going to call those objects vectors. Now, sometimes those vectors will actually be vectors, like you guys learned about in a multivariable calculus course or in geometry. Sometimes those objects might be things like matrices or polynomials or functions. If we're going to treat them as a vector space, though, even though they might be something else like a function or a matrix, we will call them a vector so that we can sort of use a name that relates all these different types of things together. So whatever those objects are, we will call them vectors. The second thing you need is you need a group of scalars, right? When you're working with vectors, you have your vectors, which are your actual objects, and then you have these sort of numbers, these scalars that are associated along with them. So we need a field of scalars. Now, a field is an important mathematical object, mathematical construct in of itself. It's not something we're discussing for our class, so we're just going to use the 2 fields that you guys have encountered in the past. Most of the time, we'll use the field of scalars that is the real numbers. Sometimes we will use the field of scalars that is the complex numbers. There are other fields out there, but that's beyond the scope of our class, so we'll be working with either the reals or the complex numbers as our scalars. A little bit of sort of terminology. If our scalars are the real numbers, then we call our vector space a real vector space. If the scalars are the complex numbers, then we call the vector space a complex vector space. So these are the 2 sort of sets that you need. You need a set of vectors and you need a set of scalars. Then you need to define some operations. You need to define a vector addition operation, which we can denote either using the standard plus sign, or if we're being a little bit more careful with our notation, we would denote it with a plus sign inside of a circle. Why do we define it in this notation? Well, sometimes this addition operation will be the standard addition that we're used to, right? The standard addition that we're used to with real valued vectors is that you add component-wise. If we were adding matrices, you know that the standard way you add matrices is you add component-wise. So a lot of times the addition operation will be the addition that we're used to. But since we're doing this very abstractly and very generally, you can actually define non-standard addition operations. So it's sort of better notation to say while it's acting like addition, it might not be the standard addition that we're used to. So we would denote that with a sort of plus inside of a circle. Same thing with scalar multiplication. We need a scalar multiplication operation, which we can denote either as a dot or a dot within a circle. Again, we would use the dot if it's the standard scalar multiplication, and we'd probably use the circle of the dot if it's a non-standard operation, so we don't confuse them. Once you've set up these 4 things, so you've got to have your 2 sets, your set of scalars and your set of vectors, and your 2 operations. How do you add vectors and how do you multiply vectors by scalars? Then you need to make sure that your 4 things follow these and satisfy these 10 properties. So these 10 properties basically ensure that the construct we're building will act the same as the sort of standard vectors that we're used to. In other words, even though the objects might not be traditional vectors, maybe they're matrices or functions or something else, they will act in the way that vectors normally act. So they have to satisfy these 10 properties. So let's talk about what each of these 10 properties sort of means. Before we do that, though, we're going to divide these properties into some categories. So these first 2 properties, we are going to reference these as closure properties. These 2 basically relate to making sure that our space is a well-defined space. And as we'll see when we start to discuss them, that basically means that if you start within the space, no matter what sort of operations you apply, you remain in that space. The next 4 operations basically make sure that the addition property works the way we imagine addition to work. So all 4 of those relate to addition. The next two, so properties 7 and 8 here, these both relate to scalar multiplication. So they basically make sure that scalar multiplication acts the way you would expect it to. And the last two both deal with the distributive property. In other words, they make sure that when you have both addition and scalar multiplication, it distributes or acts the way we would expect scalar multiplication and vector addition to work. So let's talk about what each of these properties actually means. So let's start with the closure ones. The first one says that if for any two vectors inside your vector space, if you add those two vectors, it will remain in the vector space. So in other words, if you start with two things in your vector space and you combine them together, the result will also be something in your vector space. That basically just means that your vector space is closed under addition. Adding things up won't cause you to accidentally leave the vector space. All right, let's look at property 2 then. Property 2 is closure under scalar multiplication. This one says for any vector in your vector space and for any scalar in your field of scalars, if you do your scalar with scalar multiplication and your vector, it will remain inside your vector space. So in other words, if you multiply a vector with a scalar, you will get a result that is also in your vector space. So in other words, your operation is closed under scalar multiplication. All right, let's talk about the operations for addition. The first one says that addition is going to be commutative. In other words, for any two vectors in your vector space, u plus v is the same as v plus u. So you can switch the order of addition. In other words, addition is commutative, which is something we traditionally expect about addition. All right, next one says that addition is associative, meaning that for any three vectors, you can decide to do the first vector and the second vector added together, and then take the result and add the third one. Or you can add the second and the third together, and then take the result and add that to the first. So in other words, that would be the associative property, and we want that to be true because we know addition is normally associative. The fifth property says that there is going to be something that acts as zero. So we're saying that there exists a zero vector, so we can find some vector in our vector space that acts like zero, and acting like zero means that any vector plus that zero vector will return the same vector. So u plus 0 equals u for any u in the vector space. All right, last addition property, very sort of related to the zero vector, is that there are additive inverses. So for every vector, right, in our vector space, there exists an additive inverse, which we call negative u, such that when you add the vector to its additive inverse, you get the zero vector. So we have to have additive inverses in our vector space. Later on in our next video, we will prove that this negative v actually does have to be -1 times that vector u. Or sorry, that negative u has to be that -1 times u. But actually right now, we don't know that. We're just saying that there has to be some vector that acts as the additive inverse. All right, properties 7 and 8 discuss scalar multiplication. So what properties 7 and 8 say is that the 1, so the number 1 in the real numbers or the number 1 in the complex numbers, has to act like the number 1 under scalar multiplication. So if you do 1 times any vector, you get that same vector back. So 1 really acts like 1. Then we also have the associativity of scalar multiplication. What this says is if you have any vector in your vector space and any two scalars, you can decide to choose to begin by taking one scalar times your vector and then another scalar times that, or you can multiply the scalars first and then multiply the result with the vector. Now, it is super important, and this is where the notation becomes so important here, to understand that different operations are happening here. You'll notice that on this left-hand side, this is K2 0 or circle dot u, meaning this is the scalar multiplication of K2 onto vector u. The result of this will be another vector. That's why you then have K1 circle dot the result of that, because this will again be scalar multiplication. You'll notice though on the right hand side there is no circle dot between K1 and K2, because K1 times K2 happens in the scalars. meaning this is just traditional multiplication in the reals or the complexes. So we don't need any special notation there because that'll always just be the operations we're used to because that's in the scalars, not in the vectors. And then the result of that is multiplied as a scalar onto that vector there. So that's why here there's no special operation because that multiplication is going to be in the scalars, not in our vector space. All right, the distributive properties, well, we have to make sure that a scalar distributes over addition. So k times u plus v is the same as k times u plus k times v. And same thing for if there are multiple scalars. So k1 plus k2 times u is k1 times u plus k2 times u. Notice, right, that on this guy here, once again, when you're adding k1 and k2, it's a normal plus because this addition is happening in your field of scalars, so it'll just be the normal operation. But this addition over here could be non-standard because it's an addition of these vectors. So these 10 properties are the properties that must be satisfied once you've set up your sort of two sets of objects and your two operations for something to be considered a vector space. If any one of these properties is not satisfied, then the construct you've built is not actually a vector space. Okay, so that tells you guys the definition of a vector space. In the next video, we'll actually go through property by property and show, for an example, that all 10 properties are satisfied so that the vector space that we're looking at really is a vector space. So the next video will start to have some examples and some non-examples of what is and isn't a vector space.